Welcome everyone to our weekly Astro seminar. It's a pleasure to have with us today at this very early morning time in Berkeley, Sivan Ginzburg. Sivan went to Hebrew University in Jerusalem and overlapped with me for a while, then our ways parted. He's now a postdoc at Berkeley, and he'll be talking to us about the secret life of Black Widow companions.
Okay, thanks for the introduction. Nice to see everyone here. So yes, I'll talk about the secret life of Black Widow companions, which I've been studying with Elliot Quatert. So I've already given a Black Widow talk here earlier this year, but I made some progress. So although it's the same topic, the focus of the talk will be very different. Okay, can everyone see the slides, by the way? Okay, so what are Black Widow pulsars? So pulsars are rapidly spinning and magnetized neutron stars that emit a beam of radio radiation. And as the neutron star spins around its axis, the radio beam sweeps the sky like a lighthouse. So if we have radio observers on the ground over here, they will detect the radio beam as a series of pulses every time the beam points towards the Earth. So this is why they're called pulsars. And many of these pulsars are also orbited by companions. And we can also detect the companions in the radio by their gravitational pull on the neutron star, on the primary. So as the neutron star wobbles around the center of mass, its distance from the Earth slightly changes. So this induces slight variations in the arrival time of the radio pulse to the Earth. So by measuring these variations, we can calculate both the orbital period of the companion and also its mass. And it turns out that many of these companions are very low mass. So they're only a few percent the mass of the sun. So these systems with a pulsar, a neutron star, and the low mass companion are called Black Widows. So a bit about the history of the field. So the first Black Widow was discovered in 1988 using the Arecibo radio telescope in Puerto Rico. So this is a huge dish embedded in between mountains. And they actually shot several scenes of one of the James Bond movies there, GoldenEye. So that was a surprising and exciting discovery, which has led to a lot of theoretical work in the late 80s. But not much has happened for the next 20 years. So only two other similar Black Widow systems were discovered. So these Black Widows were considered just kind of a curiosity until 2008, when the Fermi Gamma Ray telescope was launched. So these pulsars also emit gamma rays. So once Fermi was up, radio observers simply pointed their dishes towards known gamma ray emitters that Fermi found. And many of those emitters turned out to be pulsars and specifically Black Widow systems. So using this radio follow-up method of Fermi sources, more than 30 systems were detected over the last decade. And that has kind of sparked a renaissance in the theoretical study of the systems, because now there was a statistically large sample to study. And in the last couple of years, this field is going through another revolution. So up until now, all these companions were detected essentially indirectly, just by the gravitational influence on the primary, on the neutron star. But very recently, thanks to advancements in adaptive optics, we can actually finally directly image these very faint companions. And as I describe later in the talk, we can use these new optical observations to learn new things about the structure of the companion and about how it interacts with the primary, with the neutron star. Okay, so how do we think these systems formed? So according to the standard scenario, these low mass companions started their lives as much more massive, regular main sequence stars, similar to the sun. And at some point, those stars, is there a question? So at some point, those stars got close enough to the pulsar so that they overflow their Roche lobe. So just as a reminder, the companion's Roche lobe is defined as the region around the companion where the companion's gravity dominates over the tidal force of the pulsar, of the primary. So once the companion gets close enough to the star, as illustrated here, when its physical radius r exceeds the radius of its Roche lobe, which is given roughly by this condition, Then, as illustrated here, the companion overflows its Roche lobe, which means that it's being tidally stripped out of mass by the pulsar. So this is how these companions can be reduced in mass. But you can show that for Black Widow systems, this mass transfer is what we call stable. So we can show that once the companion loses a bit of mass, both its radius and the radius of its Roche lobe change in such a way that it no longer overfills its Roche lobe. So a little bit of mass transfer shuts off the overflow. This is why it's called stable. So to continue losing mass, to go actually all the way from a solar mass star to only a few percent the mass of the sun, something has to keep pushing the companion towards the pulsar. So you need to try and keep shrinking the orbit. You need to keep extracting angular momentum from the orbit of the binary. And one mechanism that extracts angular momentum is gravitational waves. So these are two massive objects on a short period orbit. So they emit gravitational waves. And similarly to the LIGO black holes, they should gradually inspire towards one another. But as you can see in the plot over here, in our case, gravitational waves are typically too weak. So here in this plot, I'm plotting the radio observables. So the x-axis is the mass of the companion. The y-axis is its orbital period. So these guys over here are the black widows. So you can see that they're typically a few percent the mass of the sun on orbits of several hours. There's also this related population of very similar but somewhat more massive objects that are nicknamed the redbacks. And this dashed pink line is the line below which companions should inspire due to gravitational waves in less than 10 gigayears, more or less the age of the universe. But you can see that for most black widows, their masses are too low and their periods are too long, so they don't inspire during their lifetimes, which means that there must be some other mechanism to extract angular momentum from the orbit. And one such mechanism can be magnetic braking. So what's magnetic braking? So stars emit winds. The sun emits a wind. Stars also generate magnetic fields. And these magnetic fields force the winds to co-rotate with them up to a radius which is called the Alfvén radius, which we can calculate. And this radius is typically much larger than the physical radius of the star. And because it's much larger, because these winds rotate material up to a large distance, it means that they can carry with them a lot of angular momentum. Even a very weak wind can carry a lot of angular momentum and significantly spin down the star. So this is how we think the sun, for example, was spun down to its very slow rotational period of about a month. And these previous papers try to invoke this magnetic braking mechanism to explain the formation of black widows. So just to be clear, the idea is that these companions are so close to the pulsars that they are tidally locked, like the moon is tidally locked to the Earth. We always see the same side of the moon. So in this case, this also happens, which means that the spin of the companion is tidally locked to its orbit. And this means that by extracting spin angular momentum, by spinning down the companion, magnetic braking also extracts angular momentum from the orbit. So very similar to gravitational waves, it pushes the companion towards Roche lobe overflow, where it can be reduced in mass. Yes.
I have two questions. So what is the Spherian radius of the sun? What's the current values?
I'm not sure. I mean, it's a simple function of the m dot, how much mass is carried by the wind, and of the sun's magnetic field. So we know both values. We know that the magnetic field is about 1 Gauss, and we know that m dot is about 10 to the minus 14 solar masses per year. But I don't remember the actual value of the Alfvén radius. But you can easily calculate it from these two values. But I don't know it on the top of my hand.
And the second question,
but it's much larger than the radius of the sun.
What? It's what?
It's much larger than the radius of the sun. I mean, we can actually, you can actually estimate it, right? Because, I mean, we know that the mass loss rate of the sun, and we know more or less its spin down rate, so we can calculate it from that either. But yeah, it's much larger than the radius of the sun.
Comparable to the radius of, let's say, Pluto's or the orbit of Mercury's orbit.
Well, you know what? Let's calculate it, right? So we know that the sun loses 10 to the 14 solar masses per year. And we know that its spin down rate is probably gigayears. So that's 10 to the 14 compared to 10 to the 9. And this ratio should be R alphen divided by the radius of the star square. So I would say that the radius of alphen divided by the radius of the star should be square root of 10 to the 14 divided by 10 to the 9. So it's square root of 10 to the 5. So this will be about 300, right? So I think the alphen radius should be about 300 times larger than the radius of the sun. So the radius of the sun is about what? It's 10 to the 11 centimeters, more or less. Yeah, so it will be times 300. So yeah, so it's about an AU. So I would say it's yeah. So I would say it's larger than the orbit of Mercury, but maybe I got something wrong in this calculation. Anyway, we can easily calculate it.
Is it something about observational consequences in terms of the solar winds that we're seeing on Earth or Venus or inner planets?
So the observational consequence is actually the spin down rate of the sun. That's the most important observational consequence, right? Because we know the rotation period of the sun today, and we know that it probably started from closer to breakup. So we know the rate at which it spins down, right?
Yeah, no, I mean, in terms of, you know, that basically what you say is that the solar wind will be also co-rotating with the sun.
Up to the alphen radius, yes.
Yeah, so does it have any consequences, you know, about satellite communications or anything like that?
It's a good question. I'm not sure. So the alphen radius, I mean, just for, yeah, so since we're talking about this, the alphen radius is determined by a very simple calculation. It's when the kinetic energy of the solar wind, rho v square, is roughly equal to the magnetic energy density in the wind, b square. But the density of the solar wind is very, very low. So rho is very, very small. Right? So basically you're asking, what you're asking is whether the solar wind is strong enough to affect satellites. And they think that we know that it's strong enough to affect satellites when it becomes stronger than nominal, right? We know that there's these solar storms, but we know that the nominal solar wind in quiescence is not, I mean, maybe it's strong enough, but we build our satellites to take this into account, right? And we know, I think there were several events, maybe in the late 80s or 90s, where there was a significant eruption of particles from the sun, which shut down the electricity in Canada, I think, or something like that. So when it's out of quiescence, we can feel it. But I think in quiescence, our instruments are already built to take this into account.
Okay, and then I have another question related to the other topic you were mentioning. So you're mentioning about the loss of angular momentum. Now, don't you have, since it's filled its Roche lobe, right? You have basically, you're forming some sort of an accretion disk. So the density inside would not be, it's not a vacuum anymore. So what about loss of angular momentum via friction with this disk?
Yeah, so we actually discussed this a lot during my previous talk here, so I don't want to get too much into this, but the idea is that it's not one dimensional, right? So you have an accretion disk around the pulsar, but it's a disk, right? And the wind comes out more spherically, so it comes in other latitudes. So there are many reasons, including the one you mentioned, for why the wind going out at, I don't know, theta equals 0 at the plane of the disk won't take angular momentum with it. There are a lot of reasons for that. But the wind coming out in other directions, which don't see the disk and don't see the pulsar, these directions are the ones that dominate the angular momentum loss.
Okay, thank you.
Okay, so anyway, yes, so I was saying that these previous studies try to explain how magnetic braking can explain the formation of black widows. But the problem with these magnetic braking relations is that they kind of incorporated the classical tradition magnetic braking relations that were calibrated observationally empirically to main sequence stars, like the sun, basically measures the stars spin down power, and from this inferring the rate of magnetic braking. But as we've just seen, these companions in our case are much less massive than main sequence stars. They also rotate much faster, and more importantly, they're being irradiated by gamma rays, by the pulsar. And these gamma rays, when they hit the companion, they drive a wind, an outflow. And while this outflow is not strong enough to significantly reduce the mass of the star, it's nonetheless much stronger than these very, very weak winds that stars emit on their own spontaneously. So because these evaporated winds are much stronger, they dominate the magnetic breaking rate. So this means that using the magnetic breaking relations for main sequence stars, using the m dots and the fields of main sequence stars is irrelevant. What you have to do, you have to solve this problem from first principles. You have to actually solve and calculate the strength of the wind and how it couples with the companion's magnetic field. So this is actually exactly was the bulk of my previous talk here. So I'm not going to repeat my previous talk. I'm going to just remind what I did for those who weren't there. So what I did then was to solve the hydrodynamics equations for the outgoing outflow, including the heating by the gamma rays and including the gravitational field of both the companion and the pulsar. So it's basically a 2D problem when you move to the rotating frame of the orbit. So when you do all this, when you solve the hydrodynamical problem, this is the final result that you get. You get the magnetic braking timescale. This is how long it will take magnetic braking to shrink the orbit, to push the companion. So it's some function of the mass and the orbital period of the companion. And just as you would intuitively expect, this timescale gets shorter the stronger the magnetic field B of the companion and the stronger the gamma ray radiation because it drives a stronger wind. So even if you did not attend my previous talk, you can see that this relation is qualitatively reasonable. It makes sense. Stronger fields and stronger irradiation drive stronger magnetic braking. And now I'm going to use this result to actually calculate the evolution of black widow companions. So here we have it. So here we have, again, the period and the mass of our companion. And let's start with a one solar mass over here, main sequence companion that fills its Roche lobe. So this will be over here. And now all we have to do is pretty simple, right? We have to reduce the mass of the companion. It's being reduced due to Roche lobe overflow. And we have to reduce the mass of the companion at a rate m dot, which is given by this magnetic braking timescale that we've just calculated, because this is the rate at which the companion is being pushed towards Roche lobe overflow. So this is all we have to do. But before I'm going to do this, I want to emphasize several points that are more general, that are valid for any arbitrary value of m dot. So that's what we have on this slide. Here we have 3 arbitrary m dot values, 10 to the 7, 10 to the 8, and 10 to the 9 yields. And the first point I want to emphasize is that since our companions always fill the Roche lobes, it means that the orbital period P is simply given by the mean density of the companion rho. So in Roche lobe overflow, you can easily show that P squared goes like 1 over G rho. So if you want to know how the orbital period evolves on this plane, all you need to know is how the mean density or the radius of the companion evolves as it loses mass. And I'm going to calculate this using the MESA stellar evolution code. I'm just going to use the single star evolution model now. I'm going to also explain analytically how to get the same results. So these are the results. This is how the period of the companion evolves as it loses mass, which are the radio observables. So now let's try and understand why do the curves look like this? Why the results look as they do? And to understand this, let's consider 2 extreme cases. So first, let's assume that the star loses mass very fast, so fast that it doesn't have time to cool down. So the gas in the star behaves adiabatically. And you can easily show that for an adiabatic ideal gas, as you decrease in mass, you also decrease in density. So the star becomes puffier, or decreases. So according to this equation, it will fill its Roche lobe at a longer orbital period. So that's why our fastest evolving track initially goes up. But what happens when the star does have time to cool down? So as the star cools down and contracts, it shrinks, right? So it becomes more dense, so rho increases, which means that the orbit shrinks, P decreases. So cooling is going down this way, going to shorter orbital periods. And in the other extreme case, if the star has an infinite amount of time to cool, it will shrink down all the way to its minimum radius, which is either on the main sequence, which is when the star is hot enough to fuse hydrogen at its center, so that prevents further contraction, or it will cool down to the degeneracy line where electron degeneracy pressure becomes large enough to prevent further contraction. And for any finite cooling time, the star will cool down to some intermediate period, which is given by this equation. So the star will cool down until the Kelvin-Helmholtz cooling time, which is a function of the period, a function of the radius, will be equal to whatever time the star had to cool down, which is in our case simply the mass loss time scale, m over m dot.
I can ask you a few questions about this plot. So first, are the dots mean anything? I mean, the star.
Oh yeah. So the dots, you mean the colored dots?
Yeah, I mean the colored dots.
Yeah. So these are So the dots are basically So they're plotted each 10 to the 7 year, 10 to the 8 years, or 10 to the 9 years, depending on which track. Okay. And because m over m dot constant, these are simply also have a constant e-folding, mass e-folding dots, right? So you lose you lose one e of your mass to here, and then another one of the e of your mass over here. And this happens over 10 to the 7 years on this track, or 10 to the 9 years on this track, for these very simple relations.
Okay, and then another question, it seems that you're using the same initial conditions. So you're using the same stars as companions. Do you have any evidence that these are always the same type of stars that begin as the companions?
Oh, that's an excellent question. Yeah. So, okay. So an answer of this. Yeah. So first of all, let's just. Yes. So the point I want to make with this plot is the first point is that the tracks here are given by this relation. The Kelvin-Helmholtz time scale is roughly given by the mass loss time scale m over m dot. And what you notice is that this condition does not depend on the history, right? It's a kind of it's a momentary condition, right? You can for any given mass and period and m dot, this will tell you exactly what the period that the star should be in, which means that you don't care about the history. And you can, we also tried this, but you can understand it from here. Even if you start from a star twice the mass of the sun, it will converge very fast to the same evolutionary track because these evolutionary tracks don't depend on the history. You simply cool down over time to satisfy this relation. So after some short adjustment time, and short will be the shorter of the initial Kelvin-Helmholtz cooling time or the initial mass loss time, then you will adjust on this scale. So that's why you can start with the same stars. Does that answer the question, Saf?
Pretty much, yeah. Okay. So you say it really doesn't matter. You could start with the different stars and it would end up pretty much doing the same thing.
Yeah, I mean, we can understand this from these analytical arguments, but I've also tried this. I also tried the stars twice the mass of the sun, and you quickly converge, due to these reasons, you quickly converge on the same flags. So there's no point in showing them.
Okay.
Okay, so the tracks on this plot are given by this equation. But you see that there's a problem here. So, okay, so maybe let's go over the tracks, for example, to be more clear. So you see that our slowest evolving track, the 10 to the 9 years, stays close to the main sequence over here. And then it reaches the hydrogen burning limit over here, and then it moves up the degeneracy line over here. But you can see that if you lose mass faster, then you can deviate from the main sequence on the blue and the red lines. So this is because the star in this case doesn't have enough time to cool down all the way to the bottom. And you see that these models pass through the observed black widow region. So nice, that's very nice, but there's actually a problem here because since Asaf asked about these markers, you can see that because these markers are separated 10 to the 8 years here or 10 to the 7 years here, you see that our models pass through the observed black widow region, but they don't stay there for long. They stay there for only a very short time. And this is actually inconsistent with the observations. So from the sheer number of observed black widows, we know that they can't be such a short-lived phase, 10 to the 7 or 10 to the 8 years. We know that they must be stable for giga years at least. So there's a problem. So the takeaway point from here is that the tracks are given by this equation. The mass loss time is equal to the Kelvin-Helmholtz cooling time. And now I'm going to focus on the cooling time to understand what's the problem over here, what's going wrong over here. And the problem here is general. It doesn't depend on the specific value of m dot. So any m dot that will bring you here will have the same timescale problem. The problem here is that the cooling time is too short, which is what we'll try to understand now. And the way I'm going to analyze the cooling times here is similar to the Hayashi track. So what's the Hayashi track? So the Hayashi track is kind of a textbook calculation that describes how very young stars, pre-main sequence stars, also cool down and contract onto the main sequence very early in their lives. And the main features on the Hayashi track that are given by the temperatures of the stars while they go to phase are that first, the opacity on the Hayashi track is dominated by the H- ion, which gives you a very steep dependence on the temperature. And the second feature is that the temperatures are such that stars on the Hayashi track are fully convective. So let's repeat this textbook calculation. How do we calculate the luminosity or the cooling rate of stars on the Hayashi track? So the way you do this, you plot this temperature versus pressure profile of the star. So this is now describing the structure inside the star. And you start at the very center of the star. So at the center of the star, the pressure and temperature are given by gravity. So this is the pressure needed to balance the gravity of the star. And this is the accompanying V-layer temperature. And now you build your temperature profile outwards by going to lower and lower pressures. So this is going outside in the star until you reach the photosphere. So the photosphere is, by definition, when the pressure is so low that the optical depth for photons to escape is about 1. So this, by definition, gives you the effective temperature of the star, which immediately gives you the luminosity of the star. So the outgoing flux is simply sigma T effective to the 4. Okay, so this is classical textbook Hayashi, a very known problem. But in our case, there's a difference. In our case, the star is being irradiated by the companion. And this irradiation changes the outer boundary condition. So it induces this outer temperature, which depends on the irradiation, which sets a flow. The star simply cannot cool down below this temperature flow. So now let's repeat the same calculation. Let's again start at the very center. And let's again follow this convective. So this because the star is fully convective, it gives you this power law adiabat. So let's follow this power law adiabatic line again. But you can see that at some point, you can't go below this floor. So what happens instead is that the star develops this outer radiative and roughly up to an order unity factor isothermal envelope, which connects to the convective interior here at this pink point at the radiative convective boundary.
I have a question.
Yes.
But you mentioned that there is a phase locking, so it's really radiating only 1/2 of the star.
Oh, excellent question. That's excellent question. Yeah. So I'll get to this later. Yeah. So maybe I'll get to this now. Yeah. So, okay, so let me get to the end of this point and then I answer a question, but that's an excellent question, yeah. So I'll get to this in 2 minutes. Yeah, so here I'm assuming that everything is 1D, but I'll get to the question soon. So in this 1D model, now the internal luminosity, how much heat is actually being evacuated from the interior is no longer determined by this T effective, but it's now given by diffusion over this radiative layer. So it will go as sigma T to the 4, divided by the optical depth of this radiative layer. So the optical depth here at the radiative convective boundary. So this is this tau RCB. And because of this steep dependence on the temperature, you will see that this will give you an inverse dependence on the temperature. So the bottom line here is that the stronger you radiate the companion, the higher this temperature is on its boundary, the lower the internal luminosity, the slower the companion will cool down. And now let's go back to Asaf's excellent question. So remember that these companions are tidally locked. So if you irradiated only once, so basically they constantly have one day side that gets all the irradiation, and they have a night side which could get nothing from the irradiation. So we see that this slows down the cooling. So if the heat stays only in the day side, you actually did nothing. You did only a factor of 2 change, right? Because you slow down the cooling on the irradiated day side, which is heated to a high temperature, but the night side still behaves like regular Hayashi. So the night side still cools much faster at this T effective. So that's why if heat is not transported from the day side to the night side, then this effect does nothing, only a factor of 2 change, which doesn't mean a lot. But as we'll see, this irradiation is actually deposited deep enough inside the atmosphere of the companion, so deep that it actually manages to be advected from the irradiated day side to the non-irradiated night side before it escapes to space. So there's a condition. You have to, there's a certain depth that you can easily calculate well, this will happen. But if you deposit there, if you deposit the energy deep enough, then the energy will be transported also to the night side. So in some sense, our model basically models the night side of the planet, which gets some, and I would claim most of the heat is being radiated to the, being transported to the night side.
Can I ask another about this equation that you're showing? There's something which I don't fully understand. The dependence on the temperature is huge, right? It goes like T to the 8, something like that, right? So you slightly change the temperature. Right, you change the temperature by a factor of 2, you end up with a factor of 100 in the luminosity. So something here I don't fully understand. Can you explain again the basic physics behind this equation?
Yeah. So basically, you're asking why the dependence on the temperature is so strong. So you can see it from over here. The dependence on the temperature is essentially, most of the dependence come from here. You have here sigma T to the 4. Right, that's simply the, if you want 80 to the 4, the energy, the radiation energy density.
Minus 8.
What?
But now it's in the denominator, so it's -8 really. From T to the 4, you went to -8.
Yeah. So maybe I went too fast. So we divide this sigma T to the 4 by the optical depth at the radiative convective boundary. Now the optical depth depends on the opacity. It's a function of the pressure and the optical depth, but it's also a function of the opacity. It's linear in the opacity. And the opacity, because it depends on the H- ion, it's a very steep function of the temperature. And this is the main feature on the Hayashi track. And the physical reason behind this, it's not actually a power law. Power is an approximation. Actually, it's an exponent. And the reason for the exponent is simply the Saha equation. You calculate the number of these H- ions, and the number of H- ions depends essentially exponentially on the temperature, right, due to the Saha equation. And usually you approximate this as this power law around the relevant temperatures. And because this is T to the 9, and here it's only T to the 4, you get about T to the -5. So it's not exactly T to the -5 because the pressure also depends on the temperature, but the -5 gives you most of this power law. Is it clear now, Asaf?
For me, yes. I don't know if the rest, but for me, yes. Thank you.
Okay, good. So anyway, the conclusion from this analytical exercise is that the pulsar's irradiation can slow down the cooling rate of the companion. And as we'll see, this will solve our problem. This will allow for long-lived black widow pulsars. So I'm going to show it now. So here we have the same evolution. We have similar evolutionary tracks. So again, period and mass. And again, I'm going to start with a 1 solar mass main sequence companion. Again, I'm going to reduce its mass, but now not arbitrarily. Now I'm reducing its mass physically by combination of magnetic braking and gravitational waves. And I'm also changing the outer boundary condition of the star to account for the pulsar's irradiation. So I'm simply changing the temperature according to the distance from the pulsar. And you can see that this solves the problem. Now our models not only pass through the black widow region, they also stay there for gigayears, which is consistent with the observations. And specifically, the models here are plotted using 2 free parameters, LMEV and L irradiation. And these 2 free parameters are related to the luminosity of the pulsar. So now you might be asking, why do I need two parameters to describe the luminosity? And the answer is that photons of different wavelengths, photons with different energies, deposit energy at different depths, different locations inside the atmosphere of the star. So to drive this wind, which drives the magnetic braking, photons must deposit their energy very high up in the atmosphere of the star, where the density of the gas is so low that it can't radiate away this heat. So instead it's being heated and accelerated to beyond the escape velocity, and it escapes the star. So this is how we form a wind. And you can show that the most efficient photons in doing so, depositing heat high up in the atmosphere of the companion, are roughly MEV photons, photons with roughly the less mass of an electron. And this is because of how the cross-section to Compton heating works. So we can show that both less energetic photons and more energetic photons than MEV deposit their energy only deeper inside the companion, where they don't contribute to this wind, but where they do contribute to slowing the cooling rate of the companion. So we have these 2 free parameters, and these are only 2 free parameters, the only parameters in the model. So the MEV luminosity, which drives the wind, and kind of the broader spectrum L irradiation, which controls the cooling rate of the star. Okay, so we have two free parameters, we have to fit them. So how do we fit our model to the observations? So it turns out that it's pretty easy. And it's easy because these parameters are roughly orthogonal. So here on this plot, I'm keeping LMEV constant, and I'm changing only L irradiation. So you see that after several gigayears, all the models reach similar masses, but very different orbital periods. So if you want to explain this span of orbital periods, this is the span of L irradiation that you need to take into account. Now I'm going to do the opposite. Now I'm keeping L irradiation constant, and I'm changing only the MEV portion of the irradiation. So now the opposite happens. Now the companions reach similar periods, but very different masses. And you would notice that the observed mass distribution has a relatively sharp cutoff right over here. You see that there are almost no companions below a few percent the mass of the sun. There are only these two outliers very far away. So if you want to reproduce this sharp cutoff in the mass distribution, this will exactly tell you which LMEV you should consider, right? Which is exactly the LMEV that we take over here. So this is how we fit our model. And we can also explain this behavior analytically. So again, our story is that we have our pulsar. It irradiates the companion with photons of different wavelengths. And we want to calculate the orbital period of the companion as it loses mass. And we've seen, I try to explain that this behavior will be given by this equation. The cooling time, the Kelvin-Helmholtz cooling time, is more or less equal to the magnetic braking time scale. So for the cooling time, I'm going to take our irradiated Hayashi model. So you remember, stronger irradiation, the stronger L irradiation, the longer this time scale. And for the magnetic braking time, I'm going to use again my results from my previous time. So a stronger field and a stronger MEV radiation causes shorter, stronger magnetic braking. Okay, so these are the ingredients. Now all I have to do is to simply equate the two. And now it's just algebra, just counting power laws. And on the right, you can see the results that we get. So the top equation will give you the shape of the evolutionary track, the period as a function of mass. You can see that the tracks are roughly horizontal. They almost don't depend on the mass. And kind of the height of the horizontal track depends mostly on L irradiation. So this equation over here explains this plot, right? So once you get to low masses, the tracks are roughly horizontal, and the height of the track, the period, depends mostly on L irradiation. And we also reproduce the right power law analytically. And the bottom equation here will give you the evolution timescale, how long it will take the companion to be reduced to some mass m. Or alternatively, given some age, let's say 10 gigayears, what will be the mass of the companion at this age? And you see that this almost does not depend on L irradiation. This depends mostly on LMEV. So there's another ingredient I haven't talked about yet, and that's the magnetic field. How do you determine the magnetic field? So magnetic fields in these companions are generated by convection. So usually you make this equipartition argument that the magnetic field, magnetic energy density is roughly equal to the kinetic energy density in the convective eddies. But because convection adjusts itself to transport some internal luminosity out from the star, it means that the magnetic field is some function of the internal luminosity, which itself is a function of L irradiation. So anyway, you can see that it gets a bit complicated, but the only point I want to make here, so we don't get lost in the equations, is that there are these two free parameters, L irradiation and LMEV, and they kind of intertwine really non-trivially together. You have to solve the equations, but once you solve the equations, you find that it turns out that very conveniently, these two free parameters kind of are orthogonal when it comes to comparing to the observables from the radio. So L irradiation mainly determines the orbital period, and LMEV mainly determines the mass at a given age. So we can analytically explain the orthogonality that we see here, also numerically. How much time do we have?
You have about 15 minutes more.
So 15 minutes, okay, 15 minutes, okay. Okay, so anyway, that's our model, both analytically and numerically. And the most important, I think the most important result that we get, and we get it both from the numerics and also from the analytics, is this, this correlation, this non-trivial correlation between a black widow's orbital period, P, and its irradiating luminosity, L irradiation. So we expect pulsars that are being irradiated with a larger luminosity to orbit at longer orbital periods. So can we test this prediction in some independent way observationally? So one thing we can do is go back to the radio. So another thing you can measure in the radio is the pulsar's spin down power. So the pulsar of the neutron star gradually slows down its rotation. It emits Larmor radiation. And this spin down is ultimately the power source that powers this irradiation. And you can see in the left panel that all black widows, and I can talk almost all, I can talk about some of the outliers later, almost all black widows generate enough spin down power to be above this relation. So we have enough energy. But we can actually do better than this. So this spin down power only gives you an upper limit to how much energy the pulsar has. Not necessarily all this energy actually goes into high energy photons that can affect the evolution of the star. So in the right panel, we make a more accurate comparison. So here we use results by the Fermi telescope. So Fermi measured actually the high energy photon luminosity, the GeV photon luminosity of a sample of these black widows. And you can see that for all of them, except for this one, for almost all of them, they generate just enough high energy photon luminosity to be exactly consistent with this relation. And I should emphasize the theory line here was not fit in any way to these observations. So both the slope and the normalization of the line were calculated purely from theory before even comparing to these observations. So the fact that the observations fit rather nicely, I think it is a confirmation at least of this part of our story. But now, and going back to Asaf's previous question, I think that using the new optical imaging, we can try and do even better than this. We can try and have an even more direct test of the theory. So if you remember Asaf's question, we have an irradiated day side because the companion side is locked, and this irradiated day side receives all the high energy photons. But as we've discussed, this energy must be transported to the night side to actually affect the evolution of the companion significantly. And now using these new optical observations, we can actually directly measure these night side temperatures. We don't need to assume anything theoretically about the efficiency of the heat transport from the day side to the night side. We can bypass these uncertainties there. We can actually directly measure the night side temperatures, which I'm comparing to over here. So you notice that these measurements are still in their infancy. They're only from the last year. And sometimes they report very large error bars. And I think there are other systematics that are not included here. But it's encouraging to see that at least those measurements with the well-constrained, at least the reported low error bars, seem to be in the right ballpark. They seem to be similar to the temperatures that we also predict from the theory. So I think that in the very near future, these direct optical observations can serve as a new, very direct and an independent test of such theories.
A question?
Yes.
Flip back. The colored lines, the purple, the blue, the red, why do these seem to terminate before actually reaching into the domain where the observations are?
Oh, okay, so excellent question. Yeah, so essentially, let's forget about the observations for a second. Let's assume that you simply have some early radiation. So if you have some early radiation, then right, a period determines the distance from the star, right? So for every early radiation, if you know the period and you know the distance from the star, you immediately know the temperature, right? So then for any early radiation, you can draw a straight line going from, I don't know, from a period of 0 to a period of infinity. So all the lines essentially go from 0 to infinity. But the trick here is that we've seen from evolutionary tracks that at the end, for any given early radiation, the period span reached by black widows is rather small, right? So if you go back here, right, for example, for this pink early radiation, you see that once you reach a low mass, a black widow mass, you only span a very small region of periods, right? Because the period correlates to early radiation. And so for the red and the blue lines, right? Once the blue line gets to low masses, it spans only a very small range of periods. So this is exactly the small range spanned here. So for every line, given any color, the evolutionary tracks will give you a very small range of periods will the black widow actually inhabit those periods given this irradiation. So this limits the temperatures that our black widows can inhabit.
Okay. But then the observations, some of them seem to be even twice as far as the allowed range.
Twice, you mean these guys?
Even the third one going up, yeah, that one, or the one to the right of that.
Yeah, yeah. So I mean, I'm much less satisfied with this fit than with this fit. It fits much worse. But I think that the main takeaway point is that both the theory and the observations seem to say that the temperatures are roughly around 3,000 Kelvin, almost regardless of the period. And I think that not every theory will give you this. This only happens because in our case, the orbital period is so strongly correlated with early radiation. So we see that when you go from the black to the pink line, you go to longer orbital periods. So imagine you didn't have this correlation, then you could have essentially the difference between the black line and the pink line continuing all the way uphill. So you would have a huge temperature difference. So the fact that the temperatures differ by only such a small factor, I think is encouraging. It goes in the right direction. I think the previous theories won't give you such a close relations. That will give you they will give you temperatures that differ by a much larger factor. But yeah, it's not a perfect fit. It's definitely not a perfect fit. Okay, so now to the last part of the talk. So I hope I convinced you so far that black widows are interesting in their own right. Now what I want to convince you is that black widows are also interesting in a much broader sense because they can be used as tools to study the structure of magnetism of stars in general. So what do I mean by that? So stars like the sun transport the heat that they generate at the center outwards, first through a radiative core and then through a convective envelope. But when you go to lower mass stars on the main sequence, when you get to below about a third of the mass of the sun, then you find that stars are fully convective. They don't have this radiative envelope. But things are very different for black widow companions. So remember that the black widows are being irradiated by the pulsar. This changes the outer boundary condition. As you remember, it means that they cool down more slowly, so they transport less heat outwards. Less heat means less convection. So we'll see that our black widow companions get to they retain the radiative cores down to much lower masses than on the main sequence. So we have this interesting structure of a radiative core, then a convective zone, and then a very thin outer radiative layer at the edge. And we also have it here. So here we have similar evolutionary tracks. And now I'm marking with this gray star the mass at which the companion becomes fully convective. So you can see that for very weak irradiation, the blue and the black lines, stars remain close to the main sequence, and they become fully convective at about 0.2 solar masses, very close to the main sequence value. But when you pump up the irradiation, when you go to the red and the pink lines, you can see that you become fully convective at a much lower mass, only a few percent the mass of the sun. This is exactly due to this effect. So in other words, on the main sequence, there's a single well-defined mass where companions become fully convective. For black widow companions, there's a variety of transition masses, all these gray stars. And you can see that the transition mass, the gray star, changes monotonically with the orbital period of the companion. So this means that by choosing the orbital period of the companion that you want to study, you can essentially control the structure. You can choose the mass at which it becomes fully convective. So this means that we can study this radiative convective transition for many new angles with many new data points in a very controlled way compared to just one data point on the main sequence. So why do we care? Why do we care about this radiative convective transition? And the answer is that we think that many stars, including the sun, actually generate their magnetic fields exactly at this boundary layer between the radiation and the convection zones. And for this reason, historically, it was believed that low mass stars, fully convective stars, cannot generate strong fields. But in recent years, we're finding more and more stars and even lower mass brown dwarfs with very strong fields. And this kind of challenges this relation between structure and magnetism. It seems that we don't fully understand magnetic fields of these low mass stars, which are the most abundant stars in the universe. And here I'm showing an example of how we can use black widows to study those magnetic fields. So here I'm arbitrarily weakening the magnetic field by some order unity factor at the gray star once the companion becomes fully convective. You can see that this slows down the evolution, the magnetic braking evolution. The 1 gigayear markers get more clusters together, and this clustering can actually fit the observed population somewhat better. It can explain why black widows cluster at these low masses, why there are essentially more black widows than these more massive leadbacks. This is just an example of how we can use black widows as tools to study magnetism in general. Okay, so I'll summarize the talk. So I named the talk The Secret Life of Black Widow Companions. And I meant this in two ways. So the first thing I meant was that up until now, all the observations, both the radio observations from the ground and the gamma ray observations from space, essentially measured the primary, the neutron star. But now, very recently, we have direct optical observations of the companions themselves. We can actually measure the luminosities, the temperatures, the radii. And the second thing I meant is that by using all of these observations, by combining them, we can learn about what happens in the interiors of these stars. It turns out that they have a very interesting structure in terms of convection versus radiation, which we can understand both analytically using the irradiated Hayashi model and also numerically using standard stellar evolution codes. And the bottom line here is that I think we can use these black widows as tools to study the magnetism of stars in general. So because these black widow companions kind of deviate, they venture from the main sequence, they give us many more data points compared to just one data point on the main sequence. And I think this will allow us to break the degeneracies in current theories of magnetic fields and magnetic braking of stars. And the magnetic braking is actually an important part of stellar evolution. So I think that this will answer several questions, both in single and in binary stellar evolution. So are there a couple of minutes left or not?
Sure.
Okay, so I try very quickly to say a few words about planets as well, only the slide. So if you have talks about planets, I'm guessing that the talks you've held, most of them at least, focused on planets that were detected indirectly. But actually the same telescopes and the same improvements in adaptive optics that allow us to directly image black widow companions also allow us to directly image more and more planets in the last years. And with Eugene Chang at Berkeley, I've been working on theories to interpret these new observations. So for example, with Martha Bryan, also from Berkeley, my office mate before this pandemic. So she's the first one to actually measure the spins of many of these directly imaged planets. So she uses rotational line broadening of high resolution spectra taken of those planets. And what I've been trying to theoretically do is to theoretically explain why do these planets rotate as slowly as they do. They rotate surprisingly slowly. And in another project with Jason Wang from Caltech, we've been studying the PDS-70 system. So this is the first system where planets were detected, PDS-70B and C, planets that are still actively accreting gas from a disk. So these are planets that are still forming, still growing in mass. And what I've been trying to do here is to theoretically translate these observed luminosities, these measured luminosities, into actual planet masses M and into accretion rates M dots. So you can ask me about these projects as well, but I'll end up here and take any further questions. Thanks.
I have a question.
Yes.
Yeah, you talked about the black widow companions. By now, I understand there are a handful of those, but there are many more stars that simply come in binaries of various types, right? Actually, most of the stars come in binaries. Now, of course, the radiation that you have from a binary might be much weaker than the one you have from a pulsar, but the orbit might be much closer in. So can you comment on those and how much the theory that you are presenting here can be valid for those objects as well?
Yeah, so actually, first of all, I would say that these binaries are pretty close. I mean, the orbits are several hours. So actually, the orbit is not much larger than the radius of the star. So actually, there are not so many close binaries, but more generally, I guess the answer is that at the end, maybe let's go here. or yeah, maybe let's start from here. So maybe let's go here. Yeah. So basically, yeah. So basically, there are two parameters that you need to compare if you want to understand whether the luminosity of the primary, in our case a pulsar, in your case another star, affects the companion. So basically, you need to compare the temperature of the star to the temperature of the irradiation. And so if the temperature of the star, so stars have their own temperature, right? The sun itself has a temperature on its own of about 6,000 Kelvin, right? So if it's being irradiated by the companion, and the companion's luminosity sets a temperature which is much below this 6,000 Kelvin, then it won't affect the companion. So what we see happens here is that the solid, so the dotted lines here give the temperature of the irradiation. So this is even a function of the luminosity of the pulsar, or in your case, some other companion, and the distance. And the solid lines give you the actual temperature of the companion. So we see that initially the companions are much hotter than the irradiation. You see that when you're one solar mass main sequence stars, even with these very luminous and very close pulsars, the temperature of the star itself, which is like the temperature of the sun, around 6,000 Kelvin, is much higher than the temperature of the irradiation. So in this phase, you actually don't feel the pulsar, you don't feel the irradiation. But only once you lose mass, only once you become low mass, only when you reach about 10% the mass of the sun, only then you start to feel the radiation. Only then your temperature becomes comparable to the temperature of the irradiation, and then you're becoming affected basically by this irradiation. So basically you have to be both low mass and very close, and the irradiation of the companion has to be very strong.
Right. I think
we'll
get into that.
So I think there are some binary stars that are mildly affected by this effect, and the effect is the same. They're slightly inflated. So there's this well-studied question that some binary stars are somewhat larger than solitary stars with the same mass. And this is exactly the explanation, right? They receive some irradiation, which slows down their cooling, so they become more inflated than normal main sequence stars. But there the effect is much smaller. They're only inflated by a few percent, maybe 10%. But here, when you go to very low black widow masses, you're actually inflated by, I don't know, by factor of 2, a factor of 3 compared to the main sequence. So I'm not aware of any binaries where the effect is larger than this, maybe 10%, except for these black widows, but maybe I'm wrong. Maybe I'm missing a whole population of relevant stars.
Okay.
Sorry for the long answer.
Any other questions? Do any of the students have any questions?
Students, please open your cameras, guys. You've got nothing to hide.
Skeletons, lots and lots of skeletons.
Guys, there's no reason to hide.
Now you can see some more of the group.
Yeah, maybe I'll unshare so I can see you all. Okay, yeah, okay. Now I see people. Nice, okay. Yeah, sorry, you can't see too many faces while you're